Welcome back. This video is going to be the final installment of our discussion on trig identities, where we're going to continue in discussing section 5.4. In the last two videos, we talked about sections 5.2 and 5.3 respectively, where we introduced a lot more trig identities and talked about how we can use them to solve for the trig value of more interesting angles, and how we can use them to verify new, more interesting trig identities than anything we thought we were able to do, say, last week. In this section, we introduce the last collection of trig identities, product to sum and sum to product formulas. Essentially, if you go back to section 5.2, we had formulas that allowed us to, so for example, start with like cosine of alpha minus b, and then turn that into some sines and cosines and their products. In this case, we're going to take those formulas, but sort of solve for products of sines and cosines instead of sines and cosines of sums and differences. So, what we gain access to are these four new trig identities, where we can use these in exactly the same way we've been trying to use trig identities this entire time. For example, what if I encounter something like the sine of 5x times the sine of 2x? The question is, what's this going to be equal to? Can I rewrite this as a sum or difference of sines, whereas I don't want to write it as a product? Well, I have a sine times a sine, so I'm going to use this first identity, and I can rewrite this as now 1/2 times the cosine of the first one minus the second one, minus the cosine of their sum, 5x plus 2x, which of course you can simplify into 1/2 times the cosine of 3x minus the cosine of 7x. And this problem, okay, maybe this doesn't actually seem like it's useful, right? I mean, all we did was take sines involving x's and turn it into something that looks more complicated. But you have to remember that the reason these trig identities exist is because there's decades worth of physicists and chemists and people who work, for example, every time you work with wave technology, if you're an engineer or something, sines and cosines pop up all the time. And you might be working with something where multiplying a bunch of sines is somehow taxing on a computer, but computing individual cosines is reasonable, and computing their difference is also reasonable. So this type of identification could take some code that's computing some sort of collection of waves for a particular product, and it could take it from an infeasible calculation to a feasible calculation just by knowing this identification. If we can do this for products of sines, of course, products of cosines are of no object either. Cosine of 7x times cosine of x, we could just rewrite that with our identity, 1/2 of cosine of the difference, 7x minus x, plus the cosine of the sum, 7x plus x, giving us 1/2 times cosine of 6x plus cosine of 8x. Now, just like these formulas up here are allowing us to take a bunch of products and rip them into sums and differences involving alpha plus or minus beta, we can take these identities and solve those to go from, instead of products to sums and differences, instead we can go from sums and differences to products. And in doing so, we can convert those four identities into these four identities. Where a very interesting one is this last one that has a negative in it. So here we're taking sums and differences of individual sines and cosines and rewriting them as products. Hence, sum to product formulas. We can do problems just like these up here, but with these formulas instead. For example, we could write sine of 7x plus sine of 3x. This can easily get rewritten as 2 times the product now of sine of their sum over 2 times cosine of their difference over 2, which you can simplify into 2 times the sine of 7 plus 3 is 10 over 2 is 5x times the cosine of 7 minus 3 is 4 over 2 is 2x. Similarly, we can add cosines together, and the formula for that would be something like 2 times the sine of the difference over 2, or the sum over 2, sorry, 3x plus 2x. Oh, my brain is having an issue. The sum of the cosines has cosines as the products. So this shouldn't be a sine at all. That should be a cosine. So we're going to get 2 times the cosine of 3x plus 2x over 2 times the cosine of the difference, 3x minus 2x over 2, which you could simplify if you'd like. These two examples might not look super useful, but you could envision a situation if you're working as an engineer or a chemist or a physicist or something like that, where you might need to know what this formula is equal to. And in particular, although right now it probably seems like using a calculator and getting a decimal for all of these things seems like the most straightforward way, and you think, oh, when I work with a real-world object, I'll only ever need to use the decimals anyway. It really will turn out that knowing how to find so-called closed forms for things like this are really going to be a lot more helpful than you think. It really helps you have a good understanding of what's happening in the background, whereas numbers like 1.2, that's not indicative of what's really happening mathematically or physically or chemically or something like that. So you might encounter something like the sine of pi over 12 minus the sine of 5 pi over 12. This is the difference of two sine waves. While using the difference formula, we can end up with rewriting this as 2 times the sine of their difference, pi over 12 minus 5 pi over 12 all over 2, times the cosine of their sum over 2, pi over 12 plus 5 pi over 12 over 2. And whereas pi over 12 is a non-standard trigonometric reference angle, observe that if I start simplifying what's inside the sine and the cosine, I'm actually getting what? Notice that pi over 12 minus 5 pi over 12 is, of course, negative pi over 4, or negative 4 pi over 12, which then when I divide by 2 gives me negative 4 pi over 24, whereas the cosine is turning into 6 pi over 24, which if I simplify these, I'm getting 2 sine of negative pi over 6 times the cosine of pi over 4, and these are reference angles that we're familiar with. This should be 2 times negative 1/2 times 1 over root 2, which of course gives negative 1 over root 2. So there is some use in these sum to product and product to sum formulas in exactly situations like this. But just like we've seen in the last few videos, whereas we can also use these identities to evaluate trig functions at values we couldn't before, we can somewhat do a little bit better with trig identities themselves. So here we have a very interesting trig identity. The left-hand side is looking very complicated, and the right-hand side looks very simple. The question is, are these in fact equal? And the answer is going to be yes, but let's see if we can't show that. We'll start with the complicated side, and we'll observe that the top is cosine minus cosine, and the bottom is sine plus sine. Those themselves have formulas. What we'll see here is that cosine of 3x minus cosine of x all over sine of 3x plus sine of x. Well, the top has a formula. That's going to be equal to negative 2 sine of the sum over 2. So that's going to be 3x plus x over 2 times the sine of the difference over 2, 3x minus x over 2, all over the sum of the sines, which is going to be 2 times sine cosine. Sine of 3x plus x over 2 times cosine of 3x minus x over 2. And on the one hand, you might think, wow, I've really overcomplicated this. You'll start to realize that, oh wait, things cancel, right? These signs are identical, so those go away. The 2's go away. And what I'm left with now is a negative sine of, let's see, 3x minus x is 2 over 2 is, of course, just an x. The bottom is a cosine of x, and we know that that's equal to negative tangent, which is where I wanted to be. So indeed, all of these identities are coming together to allow us to establish and work through and verify all sorts of additional new trigonometric identities. In a very similar vein as this identity, we have the identity on the next page, which says that the sum of the sines of two angles over the cosine of the two angles is somehow equal to tangent of their average. This is actually somewhat of an interesting identity, and it actually does have uses in other branches of science. So let's verify it real quick and make sure it's true. The left-hand side, the numerator and the denominator, are each the sum of sines and cosines respectively. So we can use sum to product formulas, and we can write and observe that sine of x plus sine of y divided by cosine of x plus cosine of y is equal to, the numerator is 2 times the sine of x plus y over 2 times the cosine of x plus y over 2. Not x plus y, we want x minus y. And the denominator, which is the sum of the cosines, will turn into 2 times the cosine of x plus y over 2 times the cosine of x minus y over 2. Where just like in the previous example, we have some nice cancellation. These cosines go out. The 2's go out. I'm left with then the top is the sine of x plus y over 2 over the cosine of x plus y over 2, which of course sine over cosine, just like last time, is the tangent of the inside, which is just x plus y over 2. And that's exactly where we want it to be. So what we see here is we see that 5.4 introduces a handful of new trigonometric identities which allow us to tackle the same types of problems but of a more varied nature. This is going to culminate and finalize our discussion on trig identities, and I'm fully aware that this is a lot of information. I know that here in sections 5.2, 5.3, and 5.4, we've introduced a whole host of different trigonometric identities and talked about other interesting applications of those identities. Take a look at the assessment list and take a look at how these trigonometric identity sections are integrated into the learning objectives, and you'll be pleasantly surprised with what you see. Next lesson will be our final lesson, and that will have us take a look at section 5.5, and that's going to be on solving trigonometric equations. The reason I said you'll be pleased with what you see is because trigonometric identities are, yes, useful in their own right, but what they're really useful for is they're useful for taking equations that involve trig functions and then simplifying them into equations that we can solve. So for example, we know how to solve equations like tangent of theta is equal to -1, find theta. We know how to do that. But what happens if this equation is way more complicated looking? Then what do we do? How do we solve for theta? It turns out that trig identities become really, really useful tools in taking very complicated equations involving trig functions and simplifying them greatly. We'll talk about that more in section 5.5 in the next set of videos, but for now, we'll finish off 5.4 here, take a look at some of the homework in the sections, let me know if you have any questions, and I will catch you all in the next one.